మేడం స్టార్ట్ చేయండి మేడం. ఒక నిమిషం మేడం స్టార్ట్ చేయండి మేడం. మేడం స్టార్ట్ చేయండి. మేడం ఏమైంది మేడం?
Okay, sir. I'm starting, sir. So just a minute. Yes, welcome to TRICE webinar classes now. So here we are dealing with our NEET EAMCET program. Okay, myself Rajeshwari madam, PGT, Physical Science from TSRS School and JC Lingampally. Okay, so day before yesterday we have started with our stereochemistry chapter. So there we have dealt with what are the different types of geometrical isomers. Okay, cis-trans isomers we have studied, and we have also studied about different conformers. Okay, so here in this class we are going to learn about calculation of number of geometrical isomers in polyenes. Polyenes means more than one double bond. Ene means more than one double bond. So here, if a compound is having more than one double bond, see here, I am writing an example here. So this is your butane, number of carbons 4 I am taking here. So here I am taking more than one double bond. Two double bonds are present. So such type of compounds, you are calling them as polyenes. Poly means many. Okay, so a compound which is having more than one double bond is known as polyenes. So how we can calculate the number of geometrical isomers in this polyenes, we are going to study now, because this is an important question for your IIT point of view. Okay, so let us see what is the first rule which we have to follow in calculating the number of geometrical isomers. So if a compound with dissimilar ends containing more than one double bond, then how we can calculate the number of geometrical isomers means it is given by the formula 2 to the power of n. Okay, so for an example, see here we have taken a 4-carbon compound with the 2 R's. This R is nothing but it may be alkyl group, may be methyl or ethyl or propyl. Okay, many alkyl groups it may be. So here these two alkyl groups, it may be different. Okay, and here we are having how many double bonds? 2 double bonds. Okay, so that means here n is the number of double bonds. So what is n? N means number of double bonds. Okay, so number of double bonds will give you the number of geometrical isomers. So here if you substitute n is equal to, how many double bonds we are having? 1 and 2. So if you substitute n is equal to 2 in the formula 2 to the power of n, okay, then we'll get here, see here, 2 to the power of n. In this case we are substituting 2 to the power of n is what? 2. So 2 square, it will give you 4. So that's why for this example we are getting 4 isomers. So it will be useful for calculation of your geometrical isomers if the compound is containing dissimilar ends. This is the condition now. Okay, so if the compound is containing dissimilar ends and more than one double bond, then we can calculate the number of geometrical isomers by using the formula 2 to the power of n, where n is equal to number of double bonds in that compound. Only these two are the number of double bonds, and here R is the alkyl groups, whether it may be 1 carbon methyl group or 2 carbons ethyl group or 3 carbons propyl group, like that, so on, depending upon the number of carbons we are taking. So it is a generalized formula, that is R is equal to your alkyl group. Okay, ma. So this is the first case, how we can calculate the geometrical isomers in the polyenes. So now let us see the next case. Okay, so here in the second case, we are calculating the compounds with the similar ends. Okay, in the first case, we have calculated with the dissimilar ends. But here we are taking similar ends and also having even number of stereo centers. Stereo centers means nothing but double bonds only. Okay, so the number of double bonds, then the number of geometrical isomers is given by the formula 2 to the power of n minus 1 plus 2 to the power of n by 2 minus 1. Okay, so here this one is 2 to the power of n by 2. 2 to the power of n by 2 and minus 1. Okay, ma. So here n is the number of double bonds. Okay, like your previous case only. So always n is the number of double bonds. So what is the example here? 2,4-butadiene. Okay, so 2,4-butadiene will have 3 isomers. So let us see how it is possible here with an example. So 2,4-butadiene means, how we can write? But means how many carbons? 4 carbons. So let us take 4 carbons here. So I'm taking 4 carbons, right? Okay. Now between second and fourth, the double bond is present at second position, second carbon and fourth carbon. So here first carbon, second carbon, third, fourth. So here between 2 and 3, the second carbon, 2 and 3, the double bond is present. Okay, one double bond. Diene means another double bond where it is present between 4. Okay, so between 4 and other. Okay, so that means here another methyl group we are taking here. Okay, so I'll take CH2 group. Okay, here 5 I'll take. Okay, pentadiene. We'll take 2,4-pentadiene. So between 4 and 5, if I'm taking means, then I'll get 2 double bonds here. So how many number of double bonds I'm getting here? 2. Okay, so substitute this n is equal to 2 in this formula. Okay, let us substitute here. Okay, so see here, 2 to the power of, instead of n, I'm taking 2 minus 1. Okay, plus again 2 to the power of n by 2 means 2 by 2, because n is here how much? N is 2. Okay, 2 by 2 minus 1. Okay, 2 to the power of 2 minus 1 is how much? 2 to the power of 1. That is nothing but 2 only. Okay, plus now 2 to the power of 2 by 2. 2 by 2 means 1. 1 minus 1 is how much? 0. So that means here you will get 2 to the power of 0. Right? So now what is the answer here? 2 plus 2 to the power of 0 you are getting. Okay, so 2 plus 2 to the power of 0, what it is? Equal to a to the power of 0 means 1. So in the same way, 2 to the power of 0 is 1. So 2 plus 1, how much you are getting? 3. So that's why this compound, okay, 2,4-pentadiene has 3 isomers. Okay, so that is the number of isomers when we are getting for the 2,4-pentadiene compound. Okay, so here we are taking the similar ends, the compounds which are having similar ends, and even number of double bonds. That means 2 bonds or 4 bonds or 6 bonds or 8 bonds, 8 double bonds. So like that we should take even number of double bonds. Okay, now let us see the next case for calculation of the geometrical isomers. Yes, the third case is the compounds with similar ends and odd number of stereoisomers. That means the odd number of double bonds. Okay, so here the formula is 2 to the power of n minus 1, same as it is like your even number of stereo centers, plus 2 to the power of n minus 1 whole divided by 2. There it was n by 2 minus 1, but here n minus 1 whole divided by 2. Okay, so this is the formula here. So here we are having the example 2,4,6 octatriene, which is having 6 isomers. So let us see how we are getting this 6 isomers. Okay. So octatriene. Oct means how many ma? 8 carbons. Right. So here we can write 8 carbons. 1, 2, 3, 4, 5, 6. Okay. Then 7 and 8. Okay. So like this we are taking 8 carbons. Okay. So between second and third, you place a double bond. Because the least priority between 2 and 3, we are giving the highest priority to the least number of carbons. So 2. That's why 2 in. Okay. Then 4 and 5. Between 4 and 5, I should place the double bond. Okay. That's why it is 4 in. Then next 6. Between 6 and 7, I should place another double bond. Okay. So here, how many number of double bonds are there in this compound? Ma? See here, yes, 3 are there. 1, 2, 3. So here, n value will be how much? N is equal to 3, right? Now substitute this n is equal to 3 in this formula, right? So here, how we will get 2 to the power of 3 minus 1 plus 2 to the power of 3 minus 1 whole divided by 2. Okay, so 2 to the power of 3 minus 1, how much? 2 square. 3 minus 1 is 2. 2 square plus again 2 to the power of 3 minus 1 is 2. 2 by 2 is how much? 1. So here we'll get 2 to the power of 1. Okay. Now by solving this, 2 square is how much? 4 plus, okay, 2 to the power of 1 is how much? 2. Okay. So 4 plus 2, how much you will get? 6. So that's why 2, 4, 6 octatriene. You are getting 6 isomers. Okay. 6 different ways we can show these geometrical isomers. We can change the position between 1 and 2, okay, and between 3 and 4, and between 5 and 6. Okay, so in that way we can change it by using this formula. So totally we'll get 6 isomers for this compound. 2, 4, 6 octatriene. Okay, ma. Now let us see some of the model questions which we are getting for the NEET, IIT, and EAMCET exams. Okay, ma. So the first question here is, how many geometrical isomers are possible for 2,4-heptadiene and 2,4-hexadiene? Okay, so here 4 geometrical isomers are possible for 2,4-heptadiene. Okay, so how means, see here, hept means how many, here diene is the formula. Okay, so that means in the formula only, in the name only, it is clearly indicating the number of double bonds is 2. No? Yes, 2. Okay, so here for 2,4-heptadiene, okay, for only 2,4-heptadiene I am solving here. See here, ma. So here 2,4-heptadiene means number of double bonds is 2. Okay, so we can use the formula 2 to the power of n. Okay, ma. So here n is equal to how much? 2, right? So 2 to the power of 2. 2 square is how much? 4. So that's why we are getting 4 geometrical isomers are possible for 2,4-heptadiene. So how to write all those geometrical isomers? We know that only 2 geometrical isomers are there, cis and trans. So in the first case, you arrange 2 double bonds for cis only. Okay, now. And in the second case, you arrange 2 double bonds for trans. So cis means, let me explain this example clearly with the arrangement of the double bonds. See here. So 2 cis and 4 cis heptadiene. That means here double bond should be present between 2 and 4 heptadiene. So hept means how many carbons? 7 carbons, right? So let us take 7 carbons here. I am taking 1. Yes, 7 carbons. Let us take 1, 2, 3, 4, 5, 6, and 7. Okay, 7 carbons you are taking. So 2 and 3, there is a double bond. Yes, and between 4 and 5, there is a double bond. Okay, so here first we have to take cis means on either side of this double bond, equal number of this same similar group should be present. Okay, so here when you are taking this double bond means this 2 methyl groups, let us take here on this carbon 2. Okay, and here I'll take another double bond, another carbon. Okay, ma. So let us take another methyl group on the third carbon. So here on the third carbon, second carbon, we are taking another methyl group, right? So now, so total how many carbons are there? See here, 5 plus 2. How many? How many? 7. Okay. Now, see here. So first what you are doing, if same groups, similar groups are present on either side of the double bond. See here, same 2 methyl groups are present. Here also 2 methyl groups are present, means cis on the same side. Okay, then you interchange towards the opposite side. Okay, then you will get trans. Then one cis and one trans, and one trans and one cis. Okay, so in that way you will get the number of geometrical isomers as 4. Okay, now let us see the next question. With the molecular formula C2F, fluorine, chlorine, bromine, iodine, how many geometrical isomers are possible? Okay, so here the answer will be 6 geometrical isomers. Okay, so why? Because here the molecular formula, here we are having different halogen groups. Okay, so we can arrange in different priority order. So here already we have seen one case in Kahn, Gold, in Gold and Krylov rules. The priority order you should get between fluorine and chlorine. Okay, fluorine is least priority should be given than chlorine. That means chlorine will get the highest priority, and iodine will get the highest priority than bromine. These are the 2 rules which we have to remember. Okay, ma. So here, how we are giving numbering? Fluorine is getting the top priority 1, and chlorine is getting the top priority 1. Fluorine is getting 2. So among iodine and bromine, iodine is getting the top priority 1, bromine you are getting 2. Okay, so 2 least groups, they are present towards one side, that means cis. Okay, and 2 top groups, they are present to the another side, same side. So it is a cis isomer. Okay, now just exchange one higher priority group and another lower priority group on this side. See here, here fluorine is the lower priority group 2, and iodine is the top priority group. Then it will become trans. Okay, ma. So in this exam, in another type of isomer, see here, between fluorine and chlorine. Okay, so both one top priority group and another least priority group, 2 and 1. This is another type. Okay, and here again top priority group and least priority group. Okay, so here top priority group and least priority group. So these 3 and 4 will become trans. Okay, 2, 3 and 4 are trans isomers. Now let us see fluorine and iodine. So here it is also a trans. Why? Because one top priority group and one least priority group is present. Okay, here fluorine is least priority group, fluorine is top priority group. Okay, so if one least priority group and top priority group are present on the same carbon, means that is a trans isomer. If same top priority groups are present, that is cis isomer. So when you are exchanging all this, totally you are getting 6 geometrical isomers. Okay, ma'am. Now let us see the next question. But2ene exhibits cis-trans isomerism. Okay, so let us write the structure of but2ene. So how many carbons? But means 4 carbons. Okay, so let us write that 4 carbons here. Yes, 4 carbons. Okay, 2ene means between 2 and 3 the double bond is present. Ene means double bond. Okay, so one double bond you are present, you are writing. Okay, now here carbon is having how many bonds for this carbon? 1, 2, 3 bonds. So that means here one hydrogen will be present. Okay, on this carbon also 1 carbon and 2 bonds. So one more bond is left over. So whatever leftover bond is there, we are writing hydrogens. So here you will get CH3 methyl groups. Okay, and here already 4 are over. So no hydrogens. Here for this carbon also no hydrogen, because all 4 hydrogens are utilized, because the carbon is tetravalent. Okay, and this carbon is having only single bond. So that's why we are writing another 3 hydrogens, right? So in this compound, cis trans isomerism is due to what? Rotation around the C3 and C4 sigma bond. Okay, so which is C3 here? We are counting from this side. Any side, if you are counting this, you'll get 1, 2, 3, and 4. Okay, and restricted rotation around C double bond C, rotation around C carbon, first carbon and second carbon bond, and rotation around second carbon and third carbon bond. Okay, so we are not totally rotating these two carbons. See here, restricted rotation around C double bond C will be the right answer. Why? Because just we are inter-exchanging this methyl group and hydrogen group. Okay, in the next case we'll take hydrogen below and methyl group above. Here also methyl group above and hydrogen. So just we are interaction about which bond? About double bond. So that's why B is the right answer. Okay, restricted rotation around C double bond C bond. Okay, then let us see the next question. Yes, which of the following cannot exhibit geometrical isomerism? Okay, so for exhibition of geometrical isomerism, compulsorily minimum 2 same groups should be present on either side of this double bond. Okay, see here in the first example, 2 A groups are present, 2 B groups are present. That means it will show geometrical isomerism. Okay, and in the second example, on first carbon you are having A and B groups, and second carbon you are having D and E groups. So this cannot show the geometrical isomerism. In the third example, you see A group and B group is there for on the first carbon, and second carbon also A and B are there. So it is also show the geometrical isomerism. And fourth example, you see AB, C double bond, C D A. So here at least AA is present. So this is also showing the geometrical isomerism because A similar two groups are present, but D and D are different, even though they are different, but because of these two A groups on each carbon, it will show geometrical isomerism as maybe cis or trans. Okay, but here totally these AB and DE are different. It cannot show the geometrical isomerism. Hence, the answer will be D. Okay, ma. So here we can show here C double bond C. 2 B groups are there now on the second carbon. So 2 B groups. Okay. And on the first carbon, we are having 2 A groups now. So 2 A groups. So this is cis isomer. So it will show the geometrical isomerism because it is a cis isomerism, which is a special type of geometrical isomerism. Okay, ma. Now let us see the second example. See here, C double bond C, right? So on first carbon, we are having A group and B group, both are there. On second carbon, we are having B group and E group. So totally all 4 groups are different. Because all 4 groups are different, we cannot show the geometrical isomerism in this compound. Hence, the answer is B. Okay, ma. Then let us see the next question. Geometrical isomers differ in position of substituents, position of double bond, C, single bond, bond length, and spatial arrangement of groups around the double bond. Okay, see here, position of substituents, that is for the structural isomers, position of double bond, that is for the positional isomers. Okay, C single bond, C bond length means that is only for the conformers and also structural isomers, but spatial arrangement of groups around the double bond, because around the double bond, how different similar groups are present or different groups are present, we are writing, right? So that's why geometrical isomers differ in the spatial arrangement of groups around the double bond. Okay, so this is the right answer. So hence the answer will be D, spatial arrangement of groups around the double bond. Okay, so next let us see the next question. So which of the following does not show geometrical isomerism? This is the question which is given for JEE Mains 2012. It is an important question. So which cannot show the geometrical isomerism? I told you just now, which is having all 4 different groups, then it cannot show the geometrical isomerism. So let us solve all these examples one by one. Okay, ma. So first example, what is it? 1,2-dichloro, 1-pentene. Okay, so here we'll take pentene. Pentene means how many carbons? 5 carbons. Yes, let us take 5 carbons. Okay, 5 carbons you are taking. Okay, so between first carbon and second carbon, you are having one double bond. Okay, sorry, one double bond because one pentene, and first and second carbon we are having chlorine substituents. So here we are having chlorine on first carbon, and second carbon also we are having chlorine, and remaining bonds you should fill up with hydrogen. See here, for first carbon 3 bonds are utilized, so last 4th bond is left out, that's why I have written hydrogen here. For second carbon, all 4 bonds are totally used up. Okay, for third carbon only 2 bonds, that's why it is CH2. Okay, and here also CH2. Okay, and here it is CH3. Okay, so here for this we can show the geometrical isomerism. How? By rotation of these bonds. So this ethyl group CH2 CH3 we can place by substituting by here CH2 CH3. Okay, so when you are substituting CH2 CH3 here you will get CH3. So we can create these 2 chlorines. If they are present on the same side, then it will become cis isomerism. If they are present opposite side, it will become trans isomerism. So that is first one will show geometrical isomerism. Then second one, 1,3-dichloropentane. It will also can show the geometrical isomerism because we can rotate about the third position double bond. Okay. Then 1,1-dichloropentene. This one cannot show the geometrical isomerism. So how? Let us see here. Okay, so 5 carbons you are taking here. Yes, we'll take 5 carbons. Okay, and for first carbon we are having 2 chlorines. First carbon we are having 2 chlorines. Okay, so here 1 hydrogen will be present. Okay, and sorry, on first carbon only we are having the dichloropentene. Okay, so double bond is present. Okay, so that means here instead of hydrogen we have to take double bond. Okay, we have to take a double bond between first and second carbon. That's why it is 1 pentene. Okay, so here we are having 2 chlorines. So we cannot rotate these chlorines towards the other side because totally this side is methyl group CH2, CH2, and CH3. Okay, so it cannot show the double bond. Okay, minimum to minimum we should have both the sides substituents of this chlorine. Okay, so that's why we cannot show the geometrical isomerism in 1,1-dichloro-1-pentene. Okay, so the answer will be C. The next question, which of the following compounds will show geometrical isomerism? Okay, so here 2-butene can show geometrical isomerism because equally we are having equal number of carbons on either side of the double bond. See here, 1 carbon on for second carbon, and for first carbon also we are having 1 methyl group. Okay, so easily we can rotate with the hydrogens. So first compound it will show the geometrical isomerism, 2-butene. Okay, propene, can it show? Yes. So what is propene? Propene means how many carbons? 3 carbons, right? So 3 carbons, let us take 3 carbons. So propene, normal propene means between 1 and 2, the triple double bond is present. Between 1 and 2, the double bond is present. Yes. Here remaining are hydrogens now. So hydrogen and hydrogen. Cis, and here one hydrogen and another one is methyl. Okay. So methyl groups are present. So here, because these two hydrogens are present towards the same side, it will show geometrical isomerism. So 1 and 3 can show the geometrical isomerism. Hence the answer is A. Okay. The next question, which of the following compounds will exhibit geometrical isomerism? So this is the question given for IIT in 2000 paper ma C here. So here, which of the following compounds will exhibit geometrical isomerism? Isomerism means whenever you look at this example, 2-butene means compulsorily it will show geometrical isomerism, whether it may be substituted with phenyl or any other functional group. So simply you can go for 1-phenyl 2-butene. It will show geometrical isomerism. Okay, ma. So this is the answer for showing the geometrical isomerism. Then next, let us see what is optical isomerism. What is optical isomerism? The substances which can rotate plane polarized light are called as optically active substances, and the property is called as optical isomerism. Okay, so that means here we are rotating the plane polarized light. Suppose if you are taking any substance here, okay, and we are passing it through a polarimeter. We'll be having an instrument called as polarimeter. So this substance, when it is passed through this polarimeter, what will happen? If it is rotating the light towards the right hand side, that is clockwise direction, means it is dextro-rotatory. Okay, so towards clockwise direction, dextro. Okay, and if it is rotating anti-clockwise direction like this, means it is levo-rotatory, levo. Okay, so in that way, the compounds which are rotating the plane polarized light towards left and right side are known as optically active substances, and the property is called as optical isomerism. Okay, ma. So here, what is, we will see what is plane polarized light. Okay, so what is plane polarized light? When an ordinary light is passed through a Nicholson prism made from calcite, and the transmitted light, all the vibrations are aligned in one perpendicular direction to the path of propagation, is known as plane polarized light. Okay, so here you are having, when ordinary light, we are taking an ordinary light and passing through the Nicholson prism. You know the prism. In your 9th and 10th class, you might have learned about prism. Okay, when you are passing it, then what will happen? All the vibrations of the substance, they'll be arranged like this in one plane. They'll be arranged in this one plane like this. In this manner, they will arrange themselves. Okay, they are arranged in this perpendicular direction to the propagation of the plane polarized light. Here the light is propagating in this direction. Okay, the light is propagating in this direction, and the vibrations are aligned in the perpendicular direction. Okay, so that is known as plane polarized light. Okay, so now we'll see what is a dextro-rotatory isomers. Okay, so let us see the definition for the dextro-rotatory. The isomer which rotates the plane polarized light towards right side or clockwise is known as dextro-rotatory, and it is represented by either D or plus sign. In this manner, inside the brackets, if we are writing plus, means it is indicating dextro, or small d if you are writing this, that is known as dextro. So let us understand with the help of an example here. So the isomer which rotates the plane polarized light towards the left side anti-clockwise direction, then it is known as levo-rotatory. We can remember here, R means dextro, right side dextro, left, L means left, and levo, L for levo. So left side levo-rotatory, and it is represented by small l and minus sign. Okay, ma. So here, what is the total dextro-rotatory compounds examples? Let us see here. Here we are taking a carbon which is having COOH group and I'm taking OH group and a CH2OH alcoholic functional group, okay, and another hydrogen group. So this carbon, it is having all 4 different groups. Okay, so here we have to give the priority according to the functional groups. So here we are having totally 3 functional groups. So what are the 3 functional groups? Acid functional group and alcohol functional group. So acid functional group will get the top priority because according to your IUPAC rules, you might have studied that acid will get the top priority. COOH is acid. Okay, that's why we are giving the numbering as 1. OH. Then after acid, you'll get alcohol's functional group, that is OH. Then CH2OH will get the 3rd priority because OH is having carbon methyl group. That's why it is CH2OH. Okay. Then 4th last priority is hydrogen. Okay. Now look at the rotation. How this rotation is occurring in this compound. So from 1, 2, 3, and 4. So this is clockwise direction, Nama. Clockwise. See here. From left to right. Left to right only we are traveling. Okay. So left to right we are traveling towards right only, clockwise direction. Hence, this compound is known as dextrorotatory. Dextro, D-glyceraldehyde. It is a glyceraldehyde compound because 2 OH groups will be present and 1 carboxylic functional acid functional group will be present. Now let us see the L-glyceraldehyde. What is L-glyceraldehyde? Levorotatory, right? So let us see here carbon with COOH functional group, okay, and here we'll take OH functional group. They are reversed. OH I am reversing to this side and hydrogen I'll reverse to the right side. Okay. So see here CH2OH as it is, and towards the right side hydrogen we are taking, right? We are taking the hydrogen. Now give the numbering again. So 1, OH will get 2, CH2OH will get 3 and 4. Once you see the rotation mark, see here. From right side, it is rotating towards the left side, right? See, from right side, it is rotating towards the left side. Because it is rotating from right side towards the left side, it is known as levorotatory and is represented by L. Okay, from left to right side, it is rotating. It is known as levorotatory compound L or CH2OH. So it is the L-glyceraldehyde compound.
Madam?
This slide, last slide. Okay, so what is the name of this compound, ma? L-glyceraldehyde. Okay. Yes. So just a small definition will finish off the session, ma. So what is the small definition we are going to study here in this next slide is specific rotation. Okay, so it is denoted by alpha. So what is specific rotation? Okay, specific rotation of the optically active compounds. It is given by the alpha to the power of lambda by T. Okay, so it is the formula given by observed angle of rotation, that is theta, by length of the polarimeter, that is L, into concentration of the solution C, which is given in grams per ml. Okay, so that means here specific rotation of all the optically active compounds. What are the optically active compounds? So just now we have seen dextrorotatory compounds and levorotatory compounds, which can rotate the plane polarized light towards the left side or right side. Left side they are rotating means they are known as levorotatory. If they are rotating towards the right side means they are known as dextrorotatory. So depending upon that rotation can be given by this formula alpha, that is known as specific rotation. So observed angle of rotation, at which angle of rotation that substance is rotating, that is given by the theta by length of the polarimeter. Just now I have shown you the instrument na polarimeter. So we have to take the length of the polarimeter into concentration of the solution. That means if the compound is 1 molar solution or 1 normal solution. Okay, so that is giving you the concentration of the solution. If you are substituting all these, I can sir, just so in this formula, if you are substituting means you'll get specific rotation. Yes, ma'am. Thank you. So tomorrow we'll continue the next